Hello everyone, my name is Mohan Changani and today I covered some amazing topic related to the machine learning. First we covered some mathematical questions and then we jump into some theoretical questions related to machine learning. So I hope you enjoy this video and then we start. Let's we start. First I share my screen, then we start. Okay, okay. So I hope my screen is visible to all. So let me start. So basically, we start with some mathematical question, then we jump on to the some theoretical questions. Okay. So our mathematical first question, like the compute the Jacobian of the following transformation. So for that, first we understand what is a Jacobian. Okay. So Jacobian is the like the important concept in the multivariable calculus. In that, so it's called also the Jacobian call as the Jacobian matrix, and it's helped to understand like the change in the input variable. So it's affected to the output variable also. Also, the Jacobian matrix represent that the rate of change of the vector values function with some like the respect to some variables. So it's particularly useful for the transform between the uh, coordinate coordination of systems. So in that, our problem statement is that compute the Jacobian of the following transformation. Okay, so let me start and get to the. So in that, let's consider that there is a x and y. There is the two like the variable in that. Okay. Two function in that. Okay. So let me start. There is a solution I create. So there is a Jacobian following the transformation and then we start. Okay. So there is a x and y. There is a two function. So Jacobian matrix two function x uv and y uv. Okay. With the two variables u and v are variables and the x and y is a function. In that there is a uv values and the variable values like uv. Okay. So in that first we take the Jacobian matrix. How the Jacobian matrix look like? So Jacobian matrix is the partial derivative of x divided by the derivative of u. Okay, first x with u and then x with y, x with v. Okay, derivative of x upon u, then x upon v. Okay, then after that there is the same for the y also, y function also. So y derivative of y also u and then derivative of y also v. Okay, so you see that there is the look like the Jacobian matrix look like that. Okay, then after Jacobian matrix look like that. So we find the Jacobian matrix by using some first we find the derivatives, partial derivative of the function, and then we get the Jacobian matrix. Okay, first we solve some derivative, partial derivative of that, and then we create the Jacobian matrix. Okay, so our problem is x is equal to b upon y, u and y is equal to u square minus 4v square. Okay. So first we find the derivative of the x first function. X is equal to v upon u. So in that first we take the partial derivative of the x is equal to vu. So in that portion we partial derivative of the x for the u condition. Okay. So for there is the values of the x v upon u, and then after that we partial derivative. So in that the v is constant in that. Okay, when we find out the x of x for the function for the u variable, then the v is the constant. So in that v is constant and the u will be changed. Okay, so u and u get the u square in that. So v is constant in that. Okay, so we find out the minus v upon u square because in both u square both are 2 and we get the u square in that. So v is constant in that condition. Okay, then after that we find out the same for the x for the v, and then in that condition what happened, there is the u is constant in that condition. When we find some partial derivative for the x with the v, so in that the is treat like the u is constant in that. So we easily see that there is a V is constant in that condition. In that condition U is constant, so we get the output like 1 upon U, because U is constant, and then we get some 1 upon U in that condition. Okay, so when we find out the partial derivative of the X with the V, then U is constant and we get the 1 by U in that condition. Okay, so there is the, we find out the partial derivative. Similar for the second function, like the find the partial derivative by for the y. So first we find out the there is the function like y is equal to is given u square minus 4v square. So let me start, and same thing we do for this y function also. So in that function we find out the partial derivative of the y with respect to u. In that condition v is constant. Okay, so when we find out the partial derivative of y for the u, so we get the 2u. Okay, because v is constant, this term is this I highlight. So in that condition what happened, this term is constant in that condition. Okay, and there is the equation, so we find out the 2u in that condition, so v is constant in that condition. Okay, so v is constant in that condition, and then after that same thing, so we get the so same one second. Okay, okay, then okay, so will we start, then we find out the one second. Okay, so let me start. Okay, so when in that condition, in that situation, we find out the partial derivative of y. So v is constant in that condition. When we find out the u, so v is constant. And then another thing, when we get the partial derivative of the y for the v, in that condition u is constant. Okay, so I hope you understand my things. So in that condition, when we partial derivative of y for v, and then the u is constant, so u is constant in that, so we can get 2 into 4, so it's the 8v minus 8v we get in that output. So we find out the derivative of b, so we get the minus 8v because u is constant in that condition. Okay, then after find out the both of the derivative of the first function and second function, then we create the Jacobian. Okay, so we get the Jacobian for the first u v upon u x is equal to v upon u. So we get the minus v upon u square and the 1 upon u, and that find out the first condition in that way. Okay, because we get, yes, in that condition, so we find out minus v for the u and the x for the v condition. Okay, and then after that we create the Jacobian matrix in that form. In that form we can create some Jacobian matrix, so we can easily understand, so we can easily think that the terms of that. So this concept is the Jacobian for over the transform by finding the partial derivative and organize them into the some matrix, and to get understand about the Jacobian, to for the analyze the how the multiple variable are interact with us. So this is the problem we solve by using Jacobian matrix. Okay, so let me jump on to second mathematical problem. So we find out the inverse of the 3 by 3 matrix. Okay, so inverse of the 3 by 3 matrix in that condition. So we find out, so this is the our problem statement I wrote in the page and pen and paper in our own, and then I upload in that. So we follow this step, so we get the inverse of the 3 by 3 matrix for this. So this the matrix is given 3 by 3 matrix like 1 minus 1 2 in that. Then after that for the inverse matrix, so there is, when we find the inverse matrix, so there is the formula of inverse matrix like a minus is equal to 1 upon det a, and into adj means the adjugated of the a, and the dta means the determinant of the matrix of a. So let me find out, uh, so every inverse matrix, first we find out the two things like dta and adj, so like the determinant of the matrix A and the adjugated of the A. So for that, and then we put those values into that formula. This is the inverse. This is the inverse formula, and then yeah. So this is the I highlight that. So this is the inverse formula. Okay. So we find this is the inverse formula. So we can put first we find out the determinant of the matrix A, and then we find out the adjugated of the A, and then we put into that formula. Okay. So let me start. Okay. So let me start how to solve. So first we find out the determinant of the matrix A. Okay. So this is the given matrix. Okay. Then we apply the determinant. So for determinant, we calculate the for the determinant the we have formula like DDA, like A in bracket EI minus FH minus B BI minus FG C DH EG. I get easy for you, so you can get not confused, get easily understand. So in our matrix, we form like that: A is equal to 1, B is equal to minus 1, C is equal to 2, D is equal to, because our matrix look like that. Okay, then we consider as like the we consider this is the A. Okay, this is a B and C, like that. This is a D. Okay, and E. Okay, I for your easily understand. Okay, A B C D E F G, like H and G, I. Okay, okay. Then we consider. Then we find out the formula and put up into that, so we can easily understand. So in that A, so our A is like that. A is 1. So we put in that position. Then EI. So E is 0 and I is our minus 1. So we put in that FH. F is our 6 and H is like the H is the 1. Okay, so we put, and so those we can put in that formula. So we get the adjugated of the A. Okay, so let me discuss how we put, so you can understand easily. So uh, okay, so let me determine. So in that we create like that. Okay, we get the A is equal to 1 position, B is equal to minus 1, C is equal to 2. Then we put into that value. Okay, so in that condition there is a 1. Okay, so A is position 1 and the 0. 0 we get the E position and the minus 1 I position. Then after that 6 is the F position and the 1. So there is the cross cross techniques work in that. Okay, there is these this is multiplied by this E is I and F is H, like that. So we put out the formula and then we find out the um, determinant of the A. So we find out the determinant of the A is 6. After calculation that we find out the determinant of the 6. Okay. Then after that, calculating the determinant, we calculating the adjugated. For the adjugated, we find out first the cofactor of the matrix. First, we find out for the adjugated matrix, we find out the cofactor of matrix, and then the cofactor of matrix inverse is the adjugated matrix. So first, we find out the cofactor of the matrix. So in that, our matrix is look like that. Our matrix is look like our matrix look like. And for the cofactor, so in cofactor first we multi in cofactor. So first in the cofactor, in that we first skip this row. Okay, first row, first column we skip, so we get the 0 6 1 minus 1. Then after that we skip the first row, second column. So then we find first row, second row, 4 6 1 0. Okay, then after that first row and third column, so we find out the 4 0 and 0 1. So this is the cofactor of the matrix. So we find out for the each of them. Okay, each of them. So let me start, so we can easily understand. So cofactor like that. So told that, okay, first we find out the cofactor of element one by one. So I have told that we skip the first row and the first column. In that, so we get the this value and get the cofactor of that matrix. So we get the -6 on that. Okay. Then after that, similar for the we skip the first row and second column. So we get the 4 and 6 0 1s, and we get the find out the -4 is the cofactor of that. This for the 1 by 3 first row third column skip, and then we find the values, and then we get the matrix of that cofactor like the 4. Okay. So it's similar for the when we skip the second column, first row, then we get element like that second row, second column we skip in that. So we get the cofactor of that all matrix, okay, all functions. So we get the 9 output in that, and those output we get for the cofactor matrix. So we put on in that. So cofactor A is like the -6 4 and 4, okay, because we get the, and then 1 -1 1, those are the cofactor coming from the this calculation, okay. Then we inverse that, transport that the matrix, transport that the matrix, transport meaning simply there is the rows, so we convert in the column. So see -6, then 4, and then 4, okay, like that. So we skip vertical into horizontal in that, okay, in transport function by using. So transport is the adjoint, so cofactor transport is the adjugated, okay, adjugated matrix. So we get the adjugated matrix and determinant also. Then we put on the calculate the inverse matrix. I already earlier said that we find out the determinant and adjugate it, and then we put on into the formula. So we calculate the inverse. So in formula we put on that DETA. So this is the 6, because this is the calculation and we get the 6. So 1/6, and the adjugated is A is like that. This. So when we multiply and calculated that, so we get that matrix. We find the matrix like that. So this is the our the uh, this is the inverse matrix of that. So this how we solve. I hope you understand like that. So we solve that problem, and there is the inverse of that matrix. Okay. So this is the portion I cover in the math section. Let me jump on to the machine learning question. So our first machine learning question is, why is logistic regression termed as a regression, not a classification? Okay. So in that condition, first we understand what is the logistic regression. So logistic regression called as the regression. There is a two sentence in that, logistic and regression. So logistic regression, both are two terms like the in that logistic regression. So regression is based on the principle of the linear regression. Okay. So it's work in linear regression. Even it used as a classification. When we use the classification, when we predicting some whether like the in the logistic regression we get the two values like 0 and 1, true false, pass fail, like that. Those condition is happen, then we in the classification, then we use the logistic regression in that condition. But when we predict some zeros and one, first we get the probability of the event. So for that probability of event is happening, when we calculate the some probability, we calculate using the linear combination of the input features. In that in linear regression, there is the combination of independent features and the target variable. So when we estimate some probability of the some event happen, so we get calculated the using the linear combination in that. Okay, for the input features, just like the regression, we get some plot some points and get the straight line. So in that condition, when we apply the probability, and the logistic regression is same like that, and we apply some function on that logistic regression to convert into 0 and 1. I use some understand, so you can better understand in that way. Okay, okay, let me start. Okay, so suppose there is the in that I draw in that. So there is a linear regression look like that. Okay, we get the actual point and predicted point in that, and we get the base fit line. Our aim is to sorry, my drawing is okay. So we get the base fit line in that condition. And when in the logistic regression, same like that, when in that probability, when we apply the probability, there is the probability is calculated using the linear combination. So linear combination we make, and then we apply the line on that, and then we applied the sigmoid function. There is the word is important, like the sigmoid function we applied on that. So sigmoid function in the logistic regression is term to convert the linear into the 0 to 1. Okay, 0 to 1 is convert for the sigmoid function, so we get the s type of curve in that situation. So we get like that curve in that situation, sigmoid curve, s type curve in that. So we told that there is a sigmoid curve. Okay, so when we sigmoid and squash the line, so we get the 0 and 1, okay, values. So its logistic regression predicts the 0 and 1, in between 0 and 1. And that's why the reason is that to call the regression is not a classification, because the model does not directly directly classify. First we perform some regression to estimate the probability, and then for the later turn into the some classification like 0 and 1. So we code model is the regression line, and that's why the name is logistic regression. So this is the term in logistic regression. We treat as term as the regression and not a classification. When we use some predictive model 0 and 1, then we use the logistic regression in that, because it's line to 0 and 1. So it's the, I hope it's clear for you. Logistic regression is term as the regression, not a classification. Yeah. Okay. Then we turn on our second question. So our second question is the multicollinearity. So multicollinearity is the important term when we learn some regression, linear regression. In that time, the multicollinearity is the important. Because of the multicollinearity is important, because we understand first what is a multicollinearity. Okay. Then we jump to the what is, first we take the what is a multicollinearity. Okay. So multicollinearity basically, if suppose we get some example, like there is the example I get, there is the CGPA, okay, like CGPA, okay, and there is the in linear regression, uh, we get the two things, independent variable and dependent variable in that. Okay, so CGPA and the IQ level, okay, and the IQ level, uh, I wrote in that. Okay, so I wrote in there. So CGPA, and the one feature is the IQ level. Okay, IQ, and second IQ, and second one is the salary of the employee. Okay, salary. So based on the salary. Okay, so based on that features, we predict based on that CGPA and IQ level, we use some salaries in these. So those problem statements we solve by using the linear regression in that. So let's happen the CGPA and IQ level are both are the independent variable. Okay, both are the independent variable. In linear regression, both are the independent variable, and one is the dependent variable is the salary, and those are the independent. But in multicollinearity, when the multicollinearities happen, when both are the independent variable, uh, both are independent variable are some highly related to each other. Like that, CGPA is highly related to the IQ. So it problem creates some problem, because in the linear regression we get some the independent features, and we get some independent feature predict some values by using the individual features, and we get the prediction of that. But in that, when multicollinearities happen, so both are, suppose there is the CGP and IQ level are same, so it's same is correlate to each, highly correlate to each other. So we told that there is a multicollinearity. So it's 90% if there is the similar of that, both are independent variables. So we told that there is a multicollinearities happen in that, because one independent feature is correlated to the both independent variable are correlated to each other, highly correlated to each other. So it's called as the multicollinearity. Like almost indicate the information of the something, and is confused, our model is confused because they are highly correlated. So that's why our model is confused and not give the good prediction in that way. So multicollinearity present, it make too hard to figure out the which how much of each variable are really contributing to the outcome, because there is the effect get mixed up. Okay, where we give some examples so you easily understand. So if we create some project, and two colleagues are the same field, same skill set, skill set, and when someone asking you create the project and who are the most contributing in that project, so then both me and my friend skill are both are match. So we get confused that how who are the most contributed in that project, so it get confused in that. So that's why in that situation there is a multicollinearities happen in that model. This is the multicollinearity concept. So yeah, it's really contribute to outcome because there are the effect to get mixed up. I already said that, and also the inflate to standard error of the coefficient and making hard to say that the sure whether variable is the truly significant. Who are the most skilled and then and effectively affected effectively work on that project. So it's get hard to say that because both skills are correlated to each other. So if you are more interested in the, and when second question is that how do you treat and when it is not a problem. Sometimes if we told that the multicollinearity is problem for every model or the sometimes, so it's no, every time multicollinearity is not affected when we some predict some model, when we simply where interest is to for the predicting some outcomes than the inputting what each variable does. So multicollinearity isn't allowed to huge problem. For example, we give example, if your model is still making the accurate prediction and despite for the multicollinearity, then you can sometime ignore it. Also you can create a field like the also we can find out the multicollinearity like we using the scatter plot. We plot the scatter plot and we find out the dotted in that, so there is a high chances of the multicollinearity happen in that situation. Also there is the scatter plot we apply in that. So those are term is the multicollinearity, and every time it's not a problem when we predict some, if we clearly predict some model, so it's it's not affected too much for that situation. Yeah, so those is cover. I hope you understand the multicollinearity variable. Then after that we move to the third question. So our third question is like that: brief explanation about the hyperparameter and optimization, the strategy and optimization strategies to perform. Okay, so we're talking about the hyperparameter optimization. So hyperparameter optimization is all about the fine tuning of setting of machine learning model before training it to get the best performance. So in simple terms, the hyperparameter is we optimize all about the fine tune. Before the training the data set, we create some assumption on that. We create some assumption and tune the setting of the machine learning model. So we get before the training. I talking the before the training. So we get the base performance on that situation. So I give some real life examples so you get easily understand what is the hyperparameter in simple terms. So if suppose we making some cookies, okay, in bakery we is making some cookies on that. So in that the hyperparameter is what how we create the cookies, there is the major portion of that the sugar level in that cookies, and those are the assumption we create for the cookies. So these are the in machine learning when we train some model, so we get first we assumption on that. So for assumption, hyperparameter optimize some strategies like the grid search. So in that you create a list of all possible combination of hyperparameter values and test each one. Okay, in the grid search we create some possible combination on the hyperparameter values, and then we test each of one, like that if possible, if we create some recipe before the making some food, so we get some recipe to get the delicious food. So in that condition, when we possible combination in the hyperparameter to eat taste the each values in the grid search. Okay, in that condition, then we're talking about the random search. Is the hyperparameter optimization random search. In that, we inside the testing every combination. We test the every combination. So you randomly pick a few combination of the test, and you testing every combination. Okay. So it's simply the different dishes, like there is a different dishes and randomly inside of the cooking every single one, like that in condition. So random forest lab inside that in the simple, so inside testing every combination and recommend the pick the few of combination in random search. Then after that we the like the Bayesian optimization. So Bayesian optimization is the approach to build a model of the performance of the hyperparameters and use the model to choose the most promising combination to the test and next. So think that we getting the feedback of our food. If we making some food and get the feedback of that, so those are, and then we apply those dish for the further. Okay, so in that Bayesian optimization, this is the approach to build a model to perform of the hyperparameter used to model to choose the most promising combination to test next. So this is the optimization technique: grid search, random search, and the Bayesian optimization. Those are the optimization. And how we know the strategy of work, in that we search the space size. If you have the many hyperparameter, so some strategy like the grid search may not work well. Also the tuning time. So if tuning time over a model takes long time, so we choose the strategy test favor option quickly. And then the resources, like the if you have limited computing power, so we get the method to are better. And the model preference, the unlimited goals, or to see the model performance new data and the better of tuning. So both are the optimization techniques in the hyperparameter. So basically, in simple term, we before the training, before any build the model, we get some assumption on that parameter assumption. In that there is the some hyper parameter like assumption, how our model are predict good, how we tune our models to get the train better and get the proper output. So both are terms I cover in this video, like the cover the three question: hyperparameter and the multicollinearity and the logistic regression, both, and the mathematical question matrix. I solve matrix like the 3 by inverse matrix, 3 by 3, and the we covering the Jacobian matrix transformation. So both are concept we cover in our video, in that video. So I hope do you understand, and thank you so much for hearing me. Yeah, bye.